Trans-4-Hydroxy-L-Prolines, protein coupled and decoupled carbon 13 NMRs. So yeah, that's a mouthful, but it's pretty cool, this stuff. So the hydroxyproline, it's an amino acid and it's an important one. It's a modified one. It got a hydroxyl group added to it, an alcohol. And it's a part of collagen. Collagen's one of the main proteins in our body. It's like a glue that holds everything together. Holds our muscles, tendons, and it's in our bones, and it's in our blood clotting. It's the most abundant protein in our bodies. And when you get older, your body produces collagen not as well, and that's why you get like wrinkles in your skin, because collagen's kind of the glue in your skin as well. And some people get collagen injections to try to keep that youthful look. Okay, so this hydroxyproline, the L, that has to do with something called stereochem. We'll talk later about it. But anyways, so this is an interesting case where first I show you the proton-coupled carbon-13 NMR. In this spectrum, we're allowing the protons with their alpha and beta spin states to couple the carbon-13s. So here first is the trans-4-Hydroxy-L-Proline, and you'll see I have a negative charge on what could be the carboxylic acid, but it's a carboxylate, and then I have a positive charge on the nitrogen here, the ammonium, which you think of amino acids. This is an amino acid as an amine and an acid, but what will happen in normal situations, the nitrogen will be protonated, so it won't be an amine, it'll be an ammonium, and the carboxylic acid will be deprotonated, so it'll be a carboxylate. So here we have it. It's overall no charge to it, but it has a plus charge and a minus charge. These are given the term Zwitter ions. You probably hear about that when you take biochem or something, but no need to worry too much about it now. Okay, so let's look at our signals. We've got a signal way down here, about like 170 way downfield. I'm going to label that 1, and you'll notice for carbon NMR, I want us all to label our carbon NMRs with numbers, starting on the left, most downfield, 1, 2, 3, like that. So we can differentiate these from our proton NMRs. Remember our proton NMRs, you label it letters A, B, C, D. So carbon NMR will use numbers, proton letters. It just makes everything more clear. We all follow the same pattern. So there's signal 2, it's a doublet. Signal 3 is a doublet. 4 is a triplet. 5 is a triplet. And the TMS over here shows up as a quartet. So let's talk about why they have these kind of coupling patterns and why this proton-coupled carbon-13 NMR is not the one that's usually run. But first, let's label the peaks. So this carbonyl carbon is number 1 here. I don't expect you to know that yet, but we'll go over things like this shortly. We'll memorize a few values, like carbonyl carbons tend to show up most downfield. And then next up, carbon 2 is the one with the alcohol, the hydroxy attached to it. That's this signal, and I don't expect you to know that, but that's what it is. And this 3 is for that one. 4 is over here, this methylene. Yep. And then, well, these are methynes to review the organic talk. And then here, another methylene. Okay, and that's it, the 5th one. And then the TMS is for, the 4 carbons of TMS are showing up there. We set that to 0. Okay, so why not just use this spectrum for a carbon NMR? Usually these splittings will occur so much that they'll start to overlap and make a big mess. This is a situation where it was set up very carefully, where you only saw short-range coupling. So, for example, let's start with carbon 1. Carbon 1 has 0 hydrogens on it, so it won't be coupled. So n plus 1 rule, 0 plus 1 would be a singlet. Carbon 2 signal has a single hydrogen on it. That hydrogen can have an alpha or beta spin state, so that gives it 2 possibilities, and that makes it a doublet. So this carbon's got the 1 neighboring hydrogen, n plus 1, 1 plus 1 is 2, there you go. And normally though, you could see, I think it's normally, I've never actually done an NMR like this, people don't normally do this. So as far as I know, so normally you would see the carbon, I think, I'm all over normally and I don't know, but sorry. So this carbon has 1 hydrogen on it. It can reach out and be coupled by those 2 hydrogens as well, this particular carbon. So if it's coupled by this hydrogen and these 2 and those 2, then it gets really messy. We'll look at an example like that next. So this one, see carbon 3 here has 1 hydrogen, so n plus 1 rule would be a doublet. There it is. Carbon 4 here has 2 hydrogens on it. So 2 hydrogens, N plus 1, 2 plus 1 is a triplet. And that's what you see, a triplet for carbon 4. Carbon 5 is the same. That methylene's got 2 hydrogens, N plus 1, 2 plus 1 is triplet. There it is. And then the TMS, it has 4 equivalent carbons in the tetrahedron around the silicon. And those 4 carbons have 3 hydrogens each. So those 3 hydrogens, 3 plus 1 would be 4, N plus 1 rule, right, would make you a quartet. Okay, so this can get really messy, so it's not normally done, but there is experiments that we do to figure out things like, oh yeah, this tells us it's a doublet, that there's 1 hydrogen on that carbon, but we won't usually do it this way. We'll usually do something called 2-dimensional NMR, which we'll talk about next semester. And so down here is oh wait, okay, so as I was saying, so this is a single peak, so it's a CH0, just like we said, if it's a single peak, because that means it has 0 neighbors, N plus 1. This is a doublet, so it's got to be a CH, 1 neighbor. Doublet, CH, CH2, CH2, CH3. So you can see CH3 right there, and then 5 is a CH2, yes. 4 is a CH2, yes. 3 is a CH, yes. 2 is a CH, and there's no hydrogens on carbon, signal 1, that's right. Okay. So now down here, this is what our NMRs will look like usually. Just a regular proton decoupled carbon 13 NMR. This is the standard way people run NMRs. So you just get single peaks for all your carbons. So your carbon signal 1 is a single peak. Your carbon signal 2 is a single peak. 3, 4, 5, and then the TMS is a single peak. So this is what we'll normally see. I'm going to tell you how that decoupling occurs shortly. You might wonder, this was pretty informative. Why don't we always do it this way? You'll see it's not always this clean. So now we'll just move on to another example of that.